Hello, welcome to Submodule 1.2. This is the second module in the DC analysis part of this course. In this submodule, we're going to learn the following things. We're going to talk about Ohm's Law, and we're going to be able to use it to solve the analysis of circuits. We are going to learn about Kirchhoffs laws, both the voltage law and the current law, and we're going to be able to apply them and use them to solve and analyze electrical circuits. We're also going to define what a single loop and a single node circuits are, and we're going again to be able to use that topology to solve for the analysis of circuits. We're going to derive how we combine resistors both in series and parallel. And finally, we're going to be able to extend that and use Kirchhoffs laws to derive the solution of voltage dividers as well as current dividers. This chapter and the analysis of circuits in it, uh, it focuses on resistors. Resistors are uh, electronic devices that by their inherent behavior, when a voltage is applied across the two leads of a resistor, they offer a resistance to the flow of currents. So we're going to when we apply a voltage uh, across the resistor, a current is going to be forced by that potential, by that pressure, by that electrical pressure. A current is going to be forced through the resistor, and the resistor is going to try to oppose that flow. And we're going to see that there is an algebraic relationship with that. The resistors come in many sizes. And the amount of resistance, their characteristic, is a function of the material that is used. Usually they can be of some type of carbon-based material. There is, however, another characteristic to resistors, which is how much power they can dissipate. And that is directly related to the physical size. So a resistor is going to uh, combine the current that is flowing through it and the voltage that is applied to it. And we're going to see that power is defined as the multiplication, as the product of the voltage across the resistor and the current that is flowing through it. And that power, that energy is going to be dissipated as heat. So there is a need for a resistor to have enough of a physical size, enough of a surface area to be able to dissipate that energy, to dissipate that heat. Otherwise, it's going to self-destruct. It's going to melt. So when you see uh, different sizes of resistors, that size is directly related to how much power they can dissipate. For example, here we have several resistors. They may have, for example, these two here, they may have the same resistance value, meaning that if you apply the same voltage across both of them, you're going to allow the same amount of current. However, the a resistor that is larger will be able to dissipate that much more power than another resistor that is smaller, such as this one. The relationship that relates the voltage that is applied across a resistor and the current that flows through it is called Ohm's law, and it's simply stated as such. We have a voltage that we apply across a resistor with a current that flows through it. So the relationship is that the voltage, with certain voltage applied to a resistor, I'm going to get a certain amount of current. And the voltage required to get certain current through a given resistor is equal to the product of the resistance and the current. Of course, where the resistance is going to be non-zero and finite. So I can say that if I have a 1 ohm resistor, this is the units for resistance. If I have a 1 ohm resistor and I apply a voltage across it, I'm going to get a flow of 1 ampere or amp. Those are the units. As I mentioned, the power relationship across a resistor is the product of the voltage and the current. So if I apply 1 volt across a resistor and the resulting current is 1 amp, then the power that is being dissipated by that resistor is going to be 1 watt. Those are the units. I can also express the power using Ohm's law. I can also express the power as the resistance times the square of the current by simply substituting V as Ri. So you can see that if I write Ri in for V here, then I will get R times I square. Similarly, if I substitute for the current, if I substitute the voltage divided by the resistance, in essence, solving for the current in this equation, so isolating the current by dividing both sides by the resistance, because I know that the resistance is greater than 0, then I get that the current through the resistor is going to be equal to the voltage across it divided by the resistance. And if I substitute that expression in this current, in the power equation, then I will get that the power is equal to the voltage squared divided by the resistance. I can also define another quantity called G and call it the conductance, which is going to be the reciprocal of the resistance with units of Siemens. And what that means is that if I have an amp that is flowing through that conductance due to 1 volt, that means that the conductance of that device is 1 Siemens. The equation for that relates these quantities is that the current through a conductance is equal to the conductance times the voltage applied to it. And similarly, the power is going to be the current square divided by the conductance, or the conductance times the voltage square. Do understand that a conductance and a resistor are the same device. It's just being expressed in different ways. And this equation is the same Ohm's law. This equation is the same Ohm's law defined with a conductance instead of a resistor or a resistance. And this equation is the power equation with a conductance defined with a conductance instead of a resistance by simply substituting G for 1 over R. Now that we have a good appreciation of how a voltage across a resistor, the current through it, and the resistor or the conductance, however we want to express it, relate to each other, we can look at how they figure in schematics. Here we see the symbol, the schematic symbol for a resistor, and here I have a voltage at these nodes of the resistor, and I can see that if I apply this voltage V, the current is always going to flow from the positive side to the negative side through the resistor. I can also see over here just the reverse, where the positive terminal of the voltage being applied is at the bottom, so therefore the current is going to flow this way through that resistor. If I see a current that is flowing this way, then I can know that this terminal D is the positive terminal and this terminal C is the negative terminal. Again, the current always is going to flow from the positive, from the highest voltage or the positive terminal through the resistor back to the what we're going to be calling the negative terminal. Other concepts that are going to be handy later on are those of short circuit and open circuit. So normally I'm going to have a voltage forcing a current through a resistor that has some value, but at the extremes of those cases, I can have a short circuit. So instead of a resistor, I'm going to have a wire with zero resistance, and that's going to be called the short circuit current. So if I have a voltage or two terminals in a circuit and I want to know what the short circuit current is, I would put a wire and connect those two terminals, and whatever current flows through that wire is going to be the short circuit current. If I have two terminals and I don't have a connection through it, and I measure the voltage across those two terminals, that's what is called the open circuit voltage. So in this case, we have short circuit current and open circuit voltage, and those concepts are going to come in handy later on during the course. Now let's look at two very important laws that are going to help us derive many relationships and circuit analysis techniques for the remainder of the course. But first, we have to define three concepts in the topology of circuits. And the topology is how the circuit looks when we draw it or when we connect it. The first concept is a node. Let's define formally a node. A node is a single connection point in a circuit that has the same voltage. So we see a node here is connecting four wires, and it's a single connection point, and since it is all connected, it's going to be at the same potential. That is the formal definition of a node. Then we also have branches. Branches are those legs of a circuit that connect to a single node. So this would be a branch of the circuit. So branches connect between nodes. This is another node over here. So this would be a branch of the circuit. This would be another branch of the circuit, and so on. And finally, let's define formally what a loop is in the topology of a circuit. A loop is any closed path along the circuit that you start at a node and end at another node without going through a node twice. So for example, here in this circuit, we have several loops. The outer here, that would be a loop here. We have also four loops here. We can also say that this is a loop. However, I cannot say that this is a loop. Why? Because I'm going then through this node twice. I'm going through this node twice, and that would not be that would fall outside the definition of a loop. Now, with those definitions, let's formally define what we mean by Kirchhoffs law by defining the first one, the Kirchhoffs Current Law, and simply stated, that says that the algebraic sum of all the branch currents in and out of a node is equal to 0. And we can express that with this equation. So the sum of all the individual branch currents in and out of the node is equal to 0. What do we mean by algebraic sum? What that means is that we're going to assign a sign to the direction of the current into the node. We're going to say that if the current is flowing into the node, it's going to have a negative sign, and if the current is flowing out of the node, it's going to have a positive sign. So when we sum these currents, when we add them together, we're going to preserve those signs according with the direction that they have in or out of the node. We're going to see some examples, but if I have a three branch connection at a node, and I have a current here, and I have two currents, so I have one current going into the node, and then these two currents flowing out of the node. I would say that I would express this current with a negative sign, and these two with positive signs, and then I would equate them to zero. The second Kirchhoff law is the Kirchhoff law of voltage, and that says that the algebraic sum of all voltages around a loop is equal to zero. So when I go around a loop, I'm going to use the algebraic sign defined as follows. The sign that I encounter across that voltage is going to be what I'm going to be using. So if I encounter a negative sign, that voltage is going to be expressed as a negative voltage. And if I encounter first a positive sign, that voltage is going to be expressed as a positive voltage. And then I'm going to add everything together, preserving those signs, and I'm going to equate it to zero. For example, if I have certain element here in this circuit, and then I have another element, and I have a third element around a loop, and I know that the sign here is negative, and this one is positive, and over here is positive and negative, and also here. When we add these three voltages algebraically, I'm going to write this one with a negative sign and this two with positive signs. Why? Because as I go around the loop in an arbitrary direction of a current, I can assume that the current is flowing this way. As I go around the loop in the direction of that current, I encounter the negative sign here first. I encounter the positive sign here first, and I encounter the positive sign here first. So I would write that minus this voltage plus this voltage plus this voltage is equal to zero. And again, we'll see examples of that later on. And here's an example. We have a voltage across two resistors, and we'll see how we use Kirchhoffs Voltage Law and Current Law and Ohm's Law to derive the equation for voltage division or a voltage divider. This circuit is called a voltage divider. So I can write and use Kirchhoffs voltage law to write the following equation. So I see minus V of t, so this voltage, because the minus is first, plus V sub R1, so the voltage across the first resistor, and I can see that is plus because I find the positive first as I go in the direction of the current, plus the voltage across the second resistor, again plus because I find the plus sign first, is equal to zero. Then I can solve for V and isolate that quantity, so I get this equation. Then I recall Ohm's law for each of the individual resistors, and I say that the voltage, the individual voltage across each of the resistors is equals to the resistance times the current. Notice that in the loop we have a single current. The current through this resistor the current through this resistor is the same. It must be the same as the current through this resistor because they are on the same branch. So I can write these two equations and substitute these voltages back in the original equation here, or the second equation. So I can substitute those voltages and I get this expression that the total voltage is equal to the resistance 1 times the current plus the resistance 2 times the current. Then I can solve for the current. I can factor out the current over here and take the sum of the two resistors, dividing the voltage, and I get that the current is equal to the total voltage divided by the sum of the resistors. So that's what we have so far. We can say that the current through the in the circuit or in the loop, that current is equal to the voltage divided by the sum of the two resistors. And remember that we got that by using Ohm's law to express that the voltage across the resistors is equal to the current times the resistance. Now, if I substitute this current back into these equations that were just the expression of Ohm's law for each of the resistors, I can say that the voltage, the individual voltage across each of the resistors is equal to that resistance divided by the total resistance times the total voltage. So in essence, we're saying how much each resistor is dividing the original voltage across it. And we're saying that that amount of voltage is proportional to the value of the resistor divided by the total resistance. So the higher the resistance is in this type of voltage division network, the higher the resistance is as a proportion of the total resistance in the circuit, the higher the voltage that is dropped across it is going to be. So again, to summarize, I can say that the voltage across resistor 1 is equal to resistance 1 divided by the sum of the resistances times the total voltage, the source voltage, and the voltage across resistor 2 is going to be resistance 2 divided by the sum of the two resistances times the total voltage. In a similar fashion, we can use Kirchhoffs Current Law to derive the analysis equation for current division. If I have a current source that is forcing current into a node with two branches with a resistor in each, I can write the following equation using Kirchhoffs current law. I can say that minus I, that's the total current, and it's minus because it's going into the node as given by the source direction here, plus the current going through resistor 1 here, plus the current going through resistor 2 is equal to 0. That is an expression of Kirchhoffs current law for this circuit. Then I can just isolate the total current, and it's going to yield that the total current is the sum of the individual branch currents. Again, using Ohm's law for each of the resistors, I can say that the current through each resistor is going to be the total voltage that is going to be developed from the node to this lower node here, from the higher node to the lower node, divided by the resistance. That's just an application of Ohm's law, or an expression of Ohm's law for each of the resistors. And I can write the same thing for resistor number 2. So current 2 is going to be equal to the voltage divided by the resistance. Then I can substitute these quantities in this equation here, in this equation, and I can say that the current, the total current, is going to be equal to the voltage divided by resistor 1 plus the voltage divided by resistor 2. And I can solve for the voltage, and I get this expression. So that's what we have so far. Here we have solved for the voltage as the current divided by the sum of the reciprocal of all the resistors in the network. If we go back to the original Ohm's law expressions for each of the individual currents, and I substitute the voltage quantity for this expression that we have here, then I know how much current we have in each of the resistors as a function of the total current and the resistors in the network. And these are the final results. I can say that the current through resistor 1 is equal to the other resistor divided by the sum of all the resistors in the network, or the two resistors in the network, times the total current. Similarly, for resistor 2, or for current 2, the current through it is the other resistor, resistor 1, divided by the sum of the two resistors times the total current. So the lower a resistor is compared to the other, the higher the current that is going to flow through it. Now let's derive how we combine multiple resistors in series. Let's say that we have a network with a voltage forcing a current through a number of resistors connected in series. This type of configuration, when we have one resistor connecting like so to an X1 and to another and to another and so on, is a series connection. What I want to know is, if I substituted all these resistors connected like this by a single one, such that if I apply the same voltage, I would get the same current, what is the value of that resistor? And we'll see that the value of that resistor is simply the sum of all the resistors. How do we get there? Well, we get there by, again, applying Kirchhoffs voltage law, and by writing the voltage equation around the loop. And we get this equation. Then substituting the voltage for each of the individual resistors using Ohm's law, we get the following equation here on the right. Then, if we divide both sides by the current, because we know that the current is non-zero, and we can divide safely by it, then we're going to get that the same voltage divided by the same current is going to be the total resistance, which is the sum of all the resistors. So again, this is that final result. So the total resistance of the series combination is the sum of all the resistors. Also, we can say that from a voltage divider perspective, the voltage across an individual resistor is that resistor divided by the total resistance times the total voltage. So that would be the voltage division equation for an individual resistor in the loop. Now let's combine multiple resistors in parallel and again use Kirchhoffs laws to derive the equivalent total resistor of any number of resistors connected in parallel. This type of connection where we have all the nodes of the resistors connected together, and then we have all the other nodes connected together, that is a parallel connection. Now to derive the that total resistance, it works to assume that we have a current source, so let's call it a test current source with a current going into that direction. That of course is going to develop a voltage across the parallel combination. So it's going to look like this. And what I want to know is if I have certain current into that network, so looking at it from this side and looking at it from this side, what is the resistor here, the total resistance that is equivalent to all that parallel combination of resistors. So we know that we're going to have a current, a voltage is going to be developed, and I want to know what the total resistance would be. So I can write, using Kirchhoffs current law, I can write an equation for this node here. Let's write an equation for that node, which is really this whole thing. This whole thing is a single node because it's a single point of connection. So I can say that the current, the total current, is going to be equal to the sum of the individual branch currents, I1, I2, all the way to IN. Then I'm going to substitute each of the branch currents by their Ohms law expression of the voltage and the resistance. So we know that each branch current is going to be the voltage, which is a single quantity because I have only two nodes. So the voltage across each of the resistors is the same because we have these single points of connection. And so I substitute the voltage divided by the resistance, which is the current through each of the branches, and I get this expression. Now if I divide both sides by the voltage, which is the current divided by the voltage, is going to be 1 over the resistance, I get this expression. So the total resistance here in this expression, the total resistance, or 1 over it, is going to be the sum of the reciprocal of the individual resistances. So if I want to know what is this total resistance, all I have to do is calculate this sum, the sum of the reciprocal of the individual resistances, take the reciprocal of that, and that's going to be the total resistance. Similarly, extending that concept to the concept of current division, I can say that the current in an individual branch is going to be the total resistance divided by the individual resistor that I am interested in times the total current. So again, the lower the resistance, the higher the portion of the current, of the overall current that is going to flow through it is going to be. What we did with resistors also works. This Kirchhoffs laws also work for sources, specifically for voltage sources. when we connect them in series, we can apply Kirchhoffs voltage law to find out what is the equivalent total voltage of all those sources. Again, we use the algebraic sum of the voltages by using the sign that we first encounter in the direction of the current. Here we have the direction of the current. So the total voltage here in this circuit would be plus V2 minus V3 plus V4 plus V5 minus V1. And when we add that algebraically, we'll get this VT. And we also can preserve R1 and R2. The current doesn't know that these two resistors are not adjacent to each other because it's a single loop. So it doesn't matter. I can rearrange the connection of all these sources and resistors in the same loop, and the behavior is going to be the same. So when I combine these 5 voltage sources, into this one, then I'm left with the 2 resistors connected in this fashion, and this circuit electrically is going to be the same as this one. In other words, I have a total voltage given by the algebraic sum of all these voltage sources by using Kirchhoffs voltage law. I have the 2 resistors, and the current is going to be the same, which is the ultimate outcome of that circuit. The same thing can be applied to combining current sources that are connected in parallel. We can say that in this node, we can say that the current flowing into the node is negative and the current flowing out of the node is positive. So we can say that the total current here, by combining these 4 current sources, is minus I1 plus I3 minus I4 plus I6. And that would be the algebraic combination of those 4 current sources. Again, we are left with R1 and R2 connected the same in parallel. And this circuit is going to be electrically the same as this larger circuit in the left. What the outcome of those 2 circuits are going to be, which is going to be the same, is that the voltage developed by the combination of those current sources, V, is going to be the same in the larger circuit as in the smaller circuit. So this concludes submodule 1.2 of the portion of the course, DC analysis. We saw and we use Ohm's law. We show how that applies to a resistor. We presented Kirchhoffs current law and Kirchhoffs voltage law, and we saw how we can use those laws to derive the equations for voltage dividers and current dividers. We defined what a loop and a node was and a branch, and we use that to derive the combination, for example, of resistors in series and resistors in parallel. And we also saw the division of voltage or voltage divider circuits and current dividers as well. And we apply that further to the combination of multiple voltage sources connected in series in a circuit as well as multiple current sources connected in parallel in a circuit.